people.
Yeah, cool.
Good.
Hello, everyone. Welcome to Paper Club. Today, Vahan is going to be talking to us about transformers applied on large-scale graphs, namely molecular data.
Thank you, Carlos. Actually, should we give talking access to everyone and then ask them to mute? Or in case you don't have the rights now and then you want to talk, please feel free to raise your hand or write in the chat. We also actively monitor the chat and we try to answer questions. The important thing is I did not write this paper. I'm just trying to facilitate conversation here. So please speak up, ask questions in whichever format you prefer. Okay. Right. So I found this paper from NeurIP's accepted list for 2020. Well, the original accepted paper is not published, but that's the one from arXiv. So if you want to find new cool papers, go to NeurIP's website, search the topic you want. In this case, I searched for transformers, and then Google the title and then find the arXiv version. Okay, so let me share the screen, and then we can, this one. Cool. First, a bit of introduction before we get into details. So this paper very conveniently covers several of topics and combines them that we had during the last few months at MPlan in the paper club. So that's the transformers, self or semi-supervised learning. We had a few sessions about those, and graph networks. We had a couple of those sessions also. So here, we are basically going to pre-train a model. We had BERT and a few versions of that. In a kind of similar way, we will train a model on a graph on graph data, and then we will use the pre-trained model on other tasks. Okay. But the key here is that during the pre-training is self-supervised, so we don't need labeled data for that, which is very important in many applications, including molecular biology. And but if anyone here, besides Arvid, has experience with molecular biology, please feel free to contribute, because this may be the first paper we present in Paper Club that is about molecular biology. And the idea is that there is very little labeled data, and but there is a lot of unlabeled data. So we want to take advantage of it. And in this paper, we will do that using pre-training techniques. Okay. A bit of introduction. So, well, I spoke about the beginnings, and well, very important. So the idea is that we can present molecules as graphs, right? And each node is an atom, and then there are links, and we will have node features and edge features. Okay, and we will use this representation to train a model. We will talk a bit more about graph neural networks, and we will mention self-supervised training in terms of, for example, BERT, but we will also cover briefly attention and transformers. Okay, so those are the three main concepts used here. So first, self-supervised pre-training. So BERT is the most famous example. They also mentioned GPT, which we haven't covered here. But again, the idea is that we have a lot of unlabeled data. In case of BERT, that's just text. There are no labels, but text has a structure, and we can use that structure to pre-train models. Okay, we do similar tricks here for molecular graphs. They also mention another work called SMILES, which is, if you look here, it's also it's also a pre-trained model, but SMILES is a sequential representation. So they basically represent the molecule graph as a sequence and use, I think, an RNN to pre-train it. There were other works to pre-train graph representations for molecules. The one they cover most in this paper is the 18 one, Hu et al. So this work uses a certain kind of pre-training. So the challenge in pre-training is to choose a good enough or representative enough pre-training model, a task, so that after pre-training your model on those objectives, we can meaningfully use them for other problems. Okay, so in Hu et al, they have 3 pre-training problems. So 2 of them are for node level. So you would train a model with objectives on the node level. So that would be context prediction for the node. And then they would use node masking. So they would mask some of the nodes and then pre-train on those. And then to also pre-train for the graph level problems, they would need to label graphs, right? So that's the main limiting part here, because labeling molecules is, well, as difficult as the original problem in the first place. So it's not very practical. Okay, so in this paper, authors argue that the methods in Hu et al. Is actually suboptimal, and then we will tackle these issues by proposing new pre-training objectives. Okay. Any comments here? Okay. So now the fun part. The algorithm is called Clover, but as you can see, they don't really know how acronyms work. So there is a long name, and they just somehow made up a cool Clover name. But the idea here is that we will do 2 types of self-supervised tasks here. Again, one is for node level, the other one is for graph level tasks. For node level tasks, we will mask a subgraph that are neighbors, that is in the neighborhood of a given node. So we will have a node, and then we will mask its neighbors, and we can go into multiple steps, right? Hops away from the node, and then we will try to predict the masked nodes using the features of the current node. Okay. As you see, we don't need any labels here. And for a graph level, we will use what's called a motif. So that's, you can think of it as a type of or a cluster of molecules, which are easy to obtain from existing data. So there are algorithms that can readily create motifs for molecules. Okay, so there is no need to label anything here. Well, it's kind of a label, but it's automatically generated. Okay. Let me check if I missed anything here.
One of the
yes.
So one of the interesting things about this is that they are, in a way, they're just copying the BERT training algorithm, right? They're just saying, well, instead of masking words, you're going to mask parts of the graph. And
yes, but there is one little difference here. I think the residual connections only are different because they use just one long-range residual link, but BERT uses just shorter ones. But yeah, other than that, it's very similar.
I don't think BERT has residual connections.
Are they masking a single atom at a time, or is it they can mask multiple atoms? Or does it not matter?
I don't know.
Okay.
They don't mention it.
They just.
What do you mean? They mask multiple?
Well, I thought if each node is an atom, and then the links between the bonds between the atoms are the edges, then I'm just curious as to how much of the graph they're masking. But from the way you both spoke of it earlier, it might be not just a single node in the graph. It might be several nodes they might mask.
Oh yes, so they mask a certain percentage, 15% or so.
Okay. Okay. Interesting.
Yeah.
Yeah, interesting.
Other comments here? No? Okay. Cool. Oh yeah, and from GNM perspective, they use a message passing network, which is it's a general way, quite a general way to represent graph neural networks. We'll get into them in a moment. Okay. Okay. First, a bit of related work, molecular representation learning. So there has been a long-standing work to learn molecular representations. So the initial ones did not use graphs. So, for example, there was work, as I mentioned before, using RNN-based models. But there were also works using convolutional networks, and then eventually graphs. So one interesting paper is graph attention network. Perhaps we could present this at Paper Club at some point. We will talk about this a bit more later. But this message passing framework is a generic way to describe how node features are passed between neighbors and aggregated together to use to predict a given node. Okay, we'll see the formula in a bit. And a bit of self-supervised learning. Well, self-supervised learning has become very common in NLP. Again, BERT is the most recent, most famous example. But there has been also work for graphs, for graph-based models. For example, there is this paper, GraphSage, that uses random walk-based proximity objective. So they take random walks on the graph and then measure proximity between node features. Okay. There were other works. There was one work that used n-gram models. So that's kind of similar to this work. And Hu et al. That I mentioned before. Okay. Should we move on to formal definitions? Cool. So, we're learning on graphs, right? We have a graph, vertices, edges, number of vertices, number of edges. Here we will study undirected graphs. So the edges don't have directions, which is the case for molecules, but not in many other applications. Okay. So here we will focus on undirected graphs. Although extending any of this work to directed graphs shouldn't be too difficult. You just will need a bit of adjustments, I guess. Right, and then each edge and each node can have a feature vector. So, for example, in molecules, if you, for example, look here, so there can be double or single edges, right? Or you can have other features on the edges. And nodes obviously have features because you might have for molecules, you have an atom. So the atom has its own features. But those are the initial embeddings, right? After training our model, we will have new embeddings for each edge and each node. And that's the goal of pre-training, really. And of course, each node has a label, which we are trying to learn. Okay? And the learning task can be classification or regression, depending on your specific problem. Yes, Carlos.
Yeah, so the question is, because there has to be some sort of mapping between a node and its embedding vector. So what do they use as the, let's say, the words? What are the words in the?
Also, it's not a word, but you would say each item would have a value, right?
So it would be like the individual elements.
Yeah,
like
so
each element will have an embedding
feature. Yeah, so it would have carbon, nitrogen, oxygen, if I'm reading this right. Yeah. It can be more complex in general, but here we look at molecules.
Okay.
Cool. And then attention. We spoke about this several times here. Just a quick reminder. So attention works over matrices of queries, keys, and values. Those are learnable, and then the attention is softmax over Q, K transpose. So there's the matrix multiplication here. Softmax is element-wise. T is the dimension of the queries and keys, and then we multiply the softmax with the V. Okay, so that's the attention operator.
Ben had his hand.
And then there is the multi-head attention.
Oh, sorry, Ben had his hand.
So, yeah, I've just got a question about how you represent graphs when there's double edges. So you usually just have an adjacency matrix n by n, with n is the number of nodes, with each element is an edge. Well, what happens when you have two edges? Or do you not use adjacency matrices at all in this?
Well, it's not really a two-edge, but it's a feature of the edge. So in the adjacency matrix, instead of one, you would put, let's say, two.
I see.
Right?
Thanks.
Or in the context of learning, you may want to make it not 1, 2, but one hot vectors, right? To keep the scales right.
Yeah, or even dense vectors, right? Like the adjacency matrix becomes a tensor. So instead of being edges times, instead of being edges squared, it becomes edges squared, and then
features
embedding dimension.
So that would be the embedding dimension for each edge, but they will also have a feature embedding separately. Make sense?
Yeah. Thanks.
Okay. Cool. And then, well, as per usual, we will use multi-headed attention. So that's basically attention with multiple heads, and then we concatenate the attentions we get from each head. Okay. Should we go into more details here? I didn't check the list. If anyone wants to go into details, please. All right, cool. And then the last bit here is the graph neural networks. Here we will use the message passing framework because it's sort of general. And here, each node or vertex, we will have a hidden state. We call it HV. And then it will be generated by aggregating hidden states of its neighbors. And neighbors can go multiple steps, right? Multiple hops away. So to look at the formula, so aggregate is some function, which can be a max, a mean, or graph attention, which is the graph attention paper I mentioned earlier. Okay, so that would be attention on each neighbor of a given node, so that maybe taking the mean or the max may not be representative enough, but you may want to learn how much attention to put on each of the neighbors. Okay, so in general we call it aggregation. And then the aggregation will be across all neighbors of a given node V. I'll talk about K in a moment, and the edges that go from V. Okay, so N is the neighborhood. Now this K is the hops, so that gives us access to nodes that are not directly linked to the current node. So we get to extend a bit further, and we will run iterations here. So we start with some initial representation, and then we will do several iterations, L iterations here, and we will do KL hops. So L represents each hop, right? So if you see, if you increase L, if you increase K, you go to the next hop, right? So you basically look at the next neighbor. And then there is the activation function with the linear term, the normal thing here. Okay.
So
any questions here?
Yeah, these weights WL. So the dimension of that matrix is going to depend on how many on the connectivity of the vertex, or is it just a fixed number and it's zeroed out?
I didn't think of that. Let's see. I think it doesn't matter, because the dimension L isn't no, the dimension of W depends on the dimension of features, right? If you multiply the matrices, am I getting this right?
So it's
because you will have to adjust the other dimension.
Yeah, it's iterative, right? So you use M to calculate H, and then for the next H you use, so for the next M you use the previous H, I guess.
Maybe you would assume a fully connected one and then leave the weights 0, or I don't actually know. They didn't mention that. I didn't think of it. Do you have any good guess?
Not really. Trying to think of the dimensions of W and M.
So M's dimensions,
I was going to say, are they limiting it by a capital L iterations? Is it just an L by L, capital L by capital L? Is this a hyperparameter that you picked beforehand?
I think the dimension L is not a dimension of W, because it's an index, right? So each WL has the same dimensions. Oh no, maybe not the same. Maybe it depends on each iteration. No, each WL has the same dimensions, I think, but the capital L is not one of them. My guess is, because L is the index here, right?
So yeah, so just below it says that WL and BL are parameters inside are shared across the KL hops within the iteration after iteration. Okay, so WL, so yeah, okay. Interesting.
So if you look at the dimension of M, let's say it's a mean or a max or whatever, would be the same dimension as the hidden state, right? Because you would take means over hidden states.
Yeah, so this aggregation, it's like a reduction operation, right? Okay.
So it's M is a vector. It's not a matrix. It's a vector of the same dimension as the features.
Okay.
Right. So then you are multiplying that vector with a matrix. So the other dimension of the matrix doesn't depend on M. So that's probably the dimension you choose.
Yeah, indeed. If for aggregate you use mean or max pooling, and I guess graph attention is similar. It doesn't matter how many elements you have in the neighborhood; they will always be collapsed to a single a single vector. Okay.
Exactly. We could guess this early because m is a small m, so it has to be a vector, right? But okay, good. And yeah, and then to continue, if you want a representation for the whole graph, you can use a readout, which is basically combining all final representations of each node to get one representation for the graph. This also can be different aggregation type operations. Okay. More comments? Okay, let's talk about the Clover framework. So here we will generate 4 embeddings, which can later be used for downstream tasks. But for simplicity, in the main paper, we will only look at one stream, so we get only 2 embeddings, node embeddings and edge embeddings. But in the appendix, they also have the second stream, which is very similar. Okay, so let's just focus on this one stream. So here we have an input graph. I'll try to make this a bit bigger. We have an input graph, okay, and then the goal is to get node embeddings and edge embeddings, okay, and learn node embeddings and edge embeddings, because originally we have embeddings which are not learned. So here there will be a linear layer, okay, and then the multi-head attention that we talked about before. This dynamic MPN is basically the idea here is that instead of doing fixed k hops, we will randomize that number k, so that to improve generalization. It's basically a regularization technique. Okay, no need to focus too much here. I think it's just randomizing the number of hops each time, so you get a bit of regularization. Well, you get the multi-head KV and QV and QK and Vs. Then there is the tension, well, the layer normalization, and then there are these 2 streams here. Okay, one stream we learn a node embedding, the other one an edge embedding, but they are very similar. Okay, there is the aggregation, as we spoke before. Here in the aggregation, we talked about nodes, but you can also have the same sort of aggregation on edges, except there we will have to change the graph to it's called linearized graph, basically to modify it so that edges become the focus of our learning, right? But it's very symmetric. Well, and then the feed forward, this is can be a very simple, fully connected network here. And then again, a layer normalization, and then we end up with an embedding. Okay, and then we can do the same thing. Oh, sorry, I forgot. There is also this long-range residual connection that comes to the concatenation layer. Okay. Yes, Carlos.
Yeah. So because we spoke before about the residual connection. So the attention is all you need paper. They have 2 residual connections, but I think they say that they're optional. And I'm pretty sure, but someone correct me if I'm wrong, that BERT does not use the residual connections, and even the state-of-the-art transformer in attention is all you need, they say that they don't use it either. So it's interesting that they actually do need it here.
Maybe they don't. Maybe they just use it because habits.
Yeah.
They do some ablation studies, but the residual connection is not there.
Yeah, interesting. Do they just use one layer, or do they stack the layers as well?
No. Huh. I think they don't, because they talk about the size of parameters. But do they? We'll get to it in a moment.
Okay.
I don't remember now. We'll get to experiments. Other comments? Okay. So you can do also the same procedure. Oh wait, there are There are chat comments. Doesn't aggregate take care of the different edges? What do you mean different edges? Can we?
I think this was related to the fact that you need to change a bit the graph when when doing the aggregate to edge.
No, so aggregate to edge, you don't need to change the graph, right? Yes, you don't need that here, but you can kind of swap the positions and end up with two streams. I'll scroll to the appendix here, right? So the difference here, as you can see, is the same thing, but in the transformer, you can have this so-called node view or edge view, right? So the edge view, you change the view and then work with the edges as in the aggregation, right? So here, maybe I can find the formulas. So for example, you can have the so here the aggregation is the summing the hidden layers of each node, but you can also do it for each edge, right? But we don't need to focus too much here because it's very similar, and you don't need all of them all the times, right? Because you are going to use one of these embeddings for your downstream task. So depending on your downstream task, you may only need one node embedding, right? It kind of depends on the downstream task, what view you prefer. Okay. Right. So that's the G transformer, the architecture here, and I mentioned dynamic message passing, where the idea is basically randomize the number of hops, and they mentioned you can do it as a uniform sample from a uniform distribution, or you can sample from a bounded normal distribution. Okay, not too interesting, I think. It's just something you do for generalization. Right, and then important part, constructing self-supervised tasks for pre-training. So here we don't have any labels. So we will construct two tasks that will help us with that we will use for pre-training. Right. So those are examples of molecules, simple, small examples, and here they show how the contextual properties work. So if you want to find an context, you want to learn the embedding for C, given embeddings of its neighbors and the edges between them. Okay, and that's the one pre-training task, self-supervised pre-training task. The other one is on a graph level, where they this one, where they use the software called RDK kit that automatically extracts motifs for a molecule. Interestingly, that's a multi-label classification. So it seems to be a common thing in molecular biology to have multiple labels, but those are done automatically. So there is no human actually labeling. And then they use this graph level task to pre-train our model for a graph level representation. Any comments here? No? Cool. And well, they mentioned here the fine tuning for downstream tasks. basically we will choose a downstream task. We will wait. Nothing new here. We already spoke about this. We will learn node level and graph level representations for a downstream task. And then the readout is to get a graph representation, but you can also use an MLP, very simple MLP, at the end to learn a graph representation from node representations. Okay, a bit of experiments. So maybe I just scroll to this table. They did a lot of experiments. One interesting thing I found here is, let me find it. They used 250 NVIDIA V100 GPUs to pre-train. They pre-trained 2 models, base and large. Well, large has more parameters. And let me find how many.
100 million for large.
100 million. Yeah, 100 million for large, 48 million for base. Okay, so those are pretty big models. It took them several days to pre-train, 4 days for the large one. So you shouldn't do this at home. But they haven't published any pre-trained models or code yet. So maybe after the paper comes out in EURIPS, they will publish it, because maybe it's not final yet. Hopefully they will, because then what's the point, right? Okay. And then they run several comparisons. So those are the data sets. They're all fairly large molecular data sets. So those are the number of molecules in each. And each molecule also has many atoms. And they used many different algorithms to compare. So the top ones are not pre-trained. Okay, so those are just like normal training algorithms. So the graph convolutions is attentive FP is an extension from graph attention networks. The other of those I'm not familiar with, to be honest. But those are here for reference. Okay, and they highlighted the state of the art for each database in gray. Okay, and then the bottom algorithms are, well, the first 2 are pre-trained algorithms. The bottom 2 are Clover algorithms. So we mentioned the Ngram and the Hu et al. Method. Obviously, Clover large outperforms all of them, sometimes by a pretty large margin. Not actually too large, but there is an improvement consistently. Base model doesn't necessarily outperform, right? Which is, it does on most cases, but not all. So these are classification problems, but they also study some regression data sets. Again, all molecules. Similar algorithms. They don't cover Hu et al. For regression, because they said the publicly available code doesn't support it, and it was too much work to adopt it, so they didn't do it. Fine, fair enough. But again, the large model outperforms all of them. Interestingly, there is one case when no, they are the same. Sorry. Oh yeah, there is one case when the base model is slightly better, because for regression, a lower is better. Here they showed the error. Okay, and in base model is a bit better somehow, which is interesting. Okay.
But sorry, the parentheses is the standard deviation, right?
Yes.
Yeah. So
I didn't mention those.
Yeah. So I mean, I don't think that's a significant. Yeah, but I don't think that's a significant difference, right?
Yeah.
They overlap a lot.
Yeah, exactly. But normally you would see a pretty big difference. But yeah,
they're basically the same performance for base and large, which is still interesting given that it has less than half the parameters.
Yep. They also say that the databases that have particularly many unlabeled data points, Grover outperforms more, which makes sense because of the self-supervised pre-training, right? Oh, thanks for answering the questions, Carlos. I missed all of those. Okay, any comments? Should we talk about ablation studies? So here we want to find out how much each component of our algorithm contributes to the learning. So the first one is the transformer actually doing a lot? To study that, they run toy data on the toy data. I assume just to save resources, but maybe there are other reasons which they don't mention here. Anyway, on a toy data set, they study well, the training curves and the validation curves with well, with a transformer. No, this one is without transformer. GIN is I want to make this right. So those are just other algorithms with different backbones instead of transformer, but they still use the pre-training. Okay, they still pre-train, except they don't use the transformer. And well, as you can see, that the curves may change a lot. Right, so we can confirm that transformer actually makes a big difference. Okay, and the dynamic algorithm, where we dynamically randomly, actually random is a better word, randomly choose the number of hops, and unsurprisingly, I guess, you can say that dynamic choice of number of hops slightly worsens the training curve, but slightly improves the loss curve, which is to show that it's a regularization tool. Okay. Oh, is GIN graphing isomorphic networks? I think so, Ineke. I actually don't know. I took it as a different algorithm, but we can find out.
I did
nope,
the search.
They don't even
they don't say
it.
Yeah.
Yep, they don't say it. So it is possible. I didn't check all these algorithms, limited time, but it could be. We can also, where is the, we can find out if it's important. Nope, I don't know. I can't find the reference either, so maybe later. Right, so there's a dynamic part, and actually that's all. Questions?
So I have a comment about the dynamic thing, which is it. So I don't know, from those curves, it doesn't seem like you gain much from the dynamic.
Well, yeah, just slightly for regularization.
Yeah, a little bit of validation loss. Do they make a comment about whether there's a computational cost to dynamically choosing the number of steps?
Well, I didn't see it, but I assume it. You can control it, right? Because more hops means more cost. But if you are sampling from a range, you might increase the maximum, and then the average would remain the same, right? So computationally, I would assume there is no difference.
Yeah. Well, they also tried on a toy data set, which And I guess I understand why they do it in a toy
Yeah.
data set, because if they need 4 days to train with 250 GPUs, it's too expensive to do an ablation study. But I can't remember which paper it was. I think it was a couple or 3 weeks ago, where they showed that their method. You presented that as well. That their method only works within a certain range of examples, of number of examples. It's the clustering to
Which paper?
the clustering for attention, and they do k-means for attention. I don't know if you remember that
When the authors were here.
Yep, that they showed that their method is only it is only useful after a certain number of examples is exceeded. So it would be interesting to see something similar here, like, well, all these methods, they work nice on this toy data set, but at scale, do they retain their properties?
Yeah, but the ablation study at such a scale is might be a bit problematic.
Yeah, well, it takes time.
Also, maybe they did it for maybe it appears in the published paper. So this is just from archive. Who knows?
Yeah. Wait and see.
Right? We can wait and see. Yeah. Other comments? Feedback. Please fill in the feedback.
I have another comment, which is about the because it seems like they are missing out on. I understand that resources are a big issue unless you are Google, but it seems like they're missing out a bit on the advantage that transformers have of creating intermediate representations. Like we said, we didn't. It doesn't say anywhere that they use more than one encoder layer, but precisely something that at least from BERT is that all the intermediate representations are actually useful as well, which sort of suggests that the transformer is learning intermediate representations that are useful for the next layer.
So I think they sort of do that, but maybe not explicitly, because if you look at this formula, this one, right? So this is an iteration over intermediate representations for each node, right? So they update the node representations during iterations. So, and these are done like within the transformer, right? So maybe it's a bit different, not extra layers, but they still update the representations.
Yeah, there's definitely something going on because if they reach like the 100 million parameters, they wouldn't do that with a single transformer layer, like off the shelf, so to speak. So there's something. There's definitely something adding parameters to the model. Yeah, it's interesting.
Yeah, this time we didn't invite the authors. Would be good to have them actually.
Yeah.
I have a request. It would be so great if someone outside M-Plan wanted to present. We haven't had external presenters in a few weeks, and we miss you. So if anyone is up for it, or can convince authors of a certain paper to present, that would be even better. But or bring the authors with you and then you present. Whatever works. We are usually very excited if anyone outside M-Plan wants to present. Please think about it. Cool. Should I stop sharing?
Sure. I have one last comment, but it doesn't relate necessarily to this paper, which is I find it funny that people are sort of forgetting of the decoder part of the transformer.
Oh, there was no decoder here. It was only the encoder.
Yeah, indeed.
There is no decoder here.
So even like we saw the vision transformer a few weeks ago, and it was also just the encoder. We saw all the variations of BERT are the encoder. This is just the encoder. So it looks like the decoder is just useful for machine translation and nothing else. Yes.
Well, yes, if you want to generate molecules, I guess then you use the decoder.
Yeah.
But we don't. Here we only want an embedding.
Yeah. So that might be interesting if someone finds a paper where they use the decoder for something other than machine translation. That would also be interesting. Okay.
Are you recording this, Carlos?
Yes. I think we can call it a day, unless there are any more comments or questions.
Just a very general question. The step where they did the pre-training, do we think they didn't include that in the ablation study or look at that? Are there any ways to tell whether that has limited performance, or to get an idea of that?
The pre-training has limited performance.
Yeah, are they limiting? No, it was just a general thought. It's very easy to shift your problem into a space that it is tractable and you can start to solve it. Yet the very steps that you did to do that might destroy data that is useful.
Right. That's, I guess, as a relevant point in the conclusions, they do mention that designing better pre-training self-supervised tasks will be a next step for future research, because this might be the first attempt to do, well, second attempt to do that, right? And yes, most probably, almost certainly, there is space to improve, and it depends on your downstream tasks, right? For other downstream tasks, you may want to modify the pre-training.
Yeah, good point. Good point.
So, for example, they here mentioned that the 3D input, using the 3D input for pre-training can be useful. They also say, oh, they do mention deeper models, right? They mentioned that as a future study, they would want to look at deeper models. So that explains why they didn't mention the multiple layers.
Yeah. Okay. Cool. Well, thank you, Vahan, for leading this very interesting paper and yet a new application of transformers. If we can give him a show of hands. Can you see the show of hands? Yeah. Show of hands.
Thank you all.
As appreciation. As usual, please do get in touch with us if you want to present a paper or there's a topic that you would like to you would like to discuss in Paper Club. We're more than happy to include your contributions in Paper Club. Otherwise, thank you very much, Vahan, again, and see you next week.
Thank you, Vahan.
See you all.
Yes.
Thanks.